Good morning, Algebra 1 CP students, and Happy New Year. Hopefully you're having a great start to your 2021. First video of the new year, and we are starting it off with a fresh, brand new topic in Algebra 1 CP. We're talking systems of equations, and specifically today, we're going to be discussing how to solve systems of linear equations by graphing. So I hope you're ready for a fresh new page, a brand new topic. We're going to get into it right now. When I say the word systems of equations, a system of equations is a term that refers to two or more equations that share the same variables. Okay, so two or more equations that share the same variables are collectively referred to as a system of equations. One important thing to note is that for a system of equations, and hopefully you're writing this down, to have a unique solution, so for a system of equations to have a unique solution, the number of variables must match the number of equations. So for a system of equations to have a unique solution, the number of variables must match the number of equations. What that means is if I have a system of two equations, right, I need to have two variables in that equation, no more and no less, for those variables to have a unique solution and be solvable. And that's what we're going to take a look at today, specifically systems of two linear equations, in which we need to find values not just for one variable, but for two variables that make both equations simultaneously true. Okay, so that's what we're really going to be taking a look at today. What I want to mention to you is the fact that we could very well explore higher orders of systems of equations, or higher degrees. If we did 3 equations, that means we'd need 3 variables. 4 equations, we'd need 4 variables for them to have a unique solution. But for our purposes in Algebra 1 CP, we're really just going to focus on two systems, or 2 equations, 2 variables, what's called a 2x2 system of equations. It's 2 by 2 because you'd say it's 2 equations, 2 variables. All right, so without any further ado, let's actually take a look at an example of a system of equations and how we would solve that system of equations by graphing. Here we go. First example. Let's take a look at y equals negative 1/3 times x plus 2 and y equals x minus 2. You may notice these look pretty familiar. These look like our y equals mx plus b functions, our slope-intercept form that we saw before. And yeah, it is pretty similar. You're going to notice that when we solve this system of equations, really all we're doing is solving 2 graphs simultaneously, as opposed to just one, right? Instead of sketching just the graph of one function, we're going to sketch the graphs of both functions and see what happens. Again, we're trying to find values for x and y that make these equations work out. So let's sketch a graph of what this actually looks like, and then we'll talk about that graph a little bit. I'm going to go a lot faster in graphing these things in slope-intercept form, because by now it's assumed that you should have a really good grasp of how to graph something in slope-intercept form at this point. All right, so we're going to go pretty quickly. I'll do the first one here in green, negative 1/3 x plus 2. Start at our y-intercept of 2 and follow the slope down 1 over 3, down 1 over 3, down 1 over 3. Could extend it in the other direction as well, going backwards, up 1 over 3. And using our ruler here to try to make it look nice and pretty, we end up with a linear function that kind of looks like this. There we go, that's pretty close. Like that. All right. Going into the second function now, we're going to try to sketch a graph of that. I'll do that one in red. y equals x minus 2, start at my y-intercept of negative 2. Follow the slope. The slope is 1, a hidden 1 in front of the x here. We're going to go up 1 and to the right 1. So we end up here. Up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. If we wanted to extend it in the opposite direction, we can go down 1, left 1. It preserves that straight line pattern. Connect them all with a nice ruler, and we'll end up with a graph that looks like this. Check that out. Very nice. And so we notice that when we sketch the graphs of both of these functions, there is one point, and exactly one point, where both of these graphs intersect, right? Do you see that? And this point, which is at the coordinate 3, 1, where again our coordinates in x, y, represents the solution to the system of equations, because this is the value for x and y that will actually satisfy both of these equations. It's the only one that shows up on the graph of both. So therefore, it must be the only solution, right? I think that makes sense to me. So notice, we could check our work by very quickly plugging in 3 for x and 1 for y in both of these equations and seeing, do they both work out? If x is 3 and y is 1, is it true that 3 minus 2 is equal to 1? Absolutely it is. If x is 3 and y is 1, is it true that negative 1/3 times 3 plus 2 is equal to 1? Well, negative 1/3 times 3 is negative 1. Negative 1 plus 2 is, in fact, 1. And so those values for x and y are the solution to the equation. Okay? Your solution would be x is equal to 3 and y is equal to 1. Or you could actually leave your solution written as an ordered pair, and you could say your solution is 3, 1. Either way, whatever works for you. Because writing it as an ordered pair implies that x is 3 and y is 1, because that's your x and that's your y. All right? So very quickly, I would say that the solution of a system of equations is represented by the intersection point on a graph. Okay? The solution of a system of equations is represented by the intersection point on a graph. And that is how you can solve systems of equations or multiple equations by graphing. We're going to learn two other methods to algebraically solve systems of equations, ones that involve not sketching a graph. But as far as the graph goes, the visual component is concerned, this is how you find those solutions. All right? Hopefully that makes sense. We're going to go through another example right now. You might be thinking to yourself, well, Mr. Giorgio, is it really just write two, instead of one graph, we now have two functions that we're graphing on the same coordinate plane? The answer is, yep, pretty much. So let's go ahead and take a look at another one and see how that works out. But that connection of the solution being the intersection point is super, super important. Okay, super, super important. Let's take a look at another one. Ready? How about if I have y equals 3x plus 2 and y equals 1/2 times x minus 3. What we're trying to do is we're trying to find values for x and y that satisfy both of these equations simultaneously. In order to do so, we can go ahead and sketch a graph and just see, well, hey, where do these things intersect? Because that intersection point will serve as the solution of the system. Okay, so let's take a look and see. Again, I'll do the first one in green. We have y equals 3x plus 2. We're going to start with our y-intercept of 2. And we're going to go up 3 over 1 to follow the slope. Up 1, 2, 3 over 1. Up 1, 2, 3, right 1. If I want to extend it to the left, which I may have to do in this problem, kind of noticing how it's getting pretty steep to that right side, I can go down 1, 2, 3, left 1. Down 1, 2, 3, left 1. Maybe like that. That should allow us to get a nice straight line pattern. Kind of like this. There we go. Not my best work, but not bad. I'll do the second one in red. Second one is y equals 1/2 times x minus 3. Again, start at my y-intercept of -3. Here's 1, 2, 3. 1/2 means I'm going to go up 1 and over 2. Correct? So following the slope, I would go up 1 over 2, up 1 over 2, up 1 over 2. Looks like if I keep going that way, we're not really getting close to an intersection point. So let me extend to the left by going down 1, left 2, down 1, left 2, down 1, left 2. And if you notice, when you go ahead and sketch your graph, that these lines do in fact intersect. And they intersect right here. That line wasn't my best work again, but that's okay. They intersect right here at this point. This coordinate is, let's see, it looks like -2, -4. Because that's where both of our lines intersect. And we would therefore say that that is the solution to my system. If x is -2 and y is -4, notice that this system of equations works out. Both of these equations are true. Your solution is -2, -4. Again, we can very quickly check that by saying if x is -2 and y is -4, is this true? Well, 1/2 times -2 is -1 minus 3 is in fact -4, so we're good there. And over here, 3 times -2 is -6 plus 2. Yep, that's -4, so we're good there as well. Okay, so it's always worth it to take that extra like 2 seconds. You could double check to make sure you solved your system correctly. All right, but again, you may notice it really just does involve graphing two functions on the same coordinate plane and seeing where they intersect, because that value is the only value for x and y that will satisfy both equations simultaneously. All right, very good. Let's look at now, we did 2 examples in slope-intercept form. Let's do 2 examples in standard form, and then we'll be able to call it a day. Oh yeah, standard form isn't going anywhere. You have to make sure you know how to graph both in slope-intercept form, that's your y equals mx plus b, and standard form, your ax plus by equals c. Ready for this one? We got 2x plus y is equal to 2, and we have 2x plus 3y is equal to -6. Okay? So again, there's really 2 ways that you could graph something in standard form. You could find the x and y intercepts and sketch the function, or you could convert it to y equals mx plus b and graph that way. All right? For our purposes here, I think I'll do this first example by finding intercepts on both of them, and then I'll do the second example by converting to y equals mx plus b for both of them. So whichever method you choose is totally fine. In fact, if you choose a different method, if you choose to convert to y equals mx plus b, then make sure that you actually get the same answers that I do here. It'd be a nice challenge to see that for yourself. But let's try to do this by finding our x and y intercepts. The first graph, again, I'll do in green. If I want to find the x-intercept of the graph, I'm going to set y equal to 0, meaning that 2x plus 0, because y is 0, should equal 2. And obviously from this, we get that x is equal to 1, right? We would get 2x is equal to 2. 2 times what equals 2? X would be 1. So our x-intercept is 1. To find our y-intercept, we'll set x equal to 0. So that would mean that 2 times 0 plus y is equal to 2. Well, this is almost just as easy because we would get from here that y is 2. Right there. And we would notice from that that we could kind of follow this slope, so to speak, and continue to sketch our line. Let me just move this here. Connect these two together. It's going to extend our line to kind of look like this. There we go. First line done. Notice I went through that a lot faster now because, again, we had our whole unit on graphing. It's assumed that you know how to graph something in standard form. If you're uncomfortable on that, please, please, please let me know, because that's like the crux of all of this. So that's the real focal point. If you can't do that, then it's going to be an uphill climb. All right, make sure you're comfortable with that. Second one I'll do in red here. Again, to find the x-intercept, I will set y equal to 0. That gives us, let's see, 2x plus 3 times 0 should equal -6. Well, 3 times 0 is just 0, which means we get 2x equals -6. Or in other words, x is negative 3. So here we have x is negative 1, 2, 3. Let's see our y-intercept. Let's set x equal to 0 in order to do that. That gives us that 2 times 0 plus 3y should equal negative 6. Well, if 3y is equal to negative 6, then clearly y would equal negative 2, because 3 times negative 2 is negative 6. So that puts us where? 1, 2, right here. And now I'm just going to connect these together. Notice I'm trying to be nice and neat as I do so. Try to join these just like this. And there we go. And once we connect both of these graphs, you notice, ooh, there's a spot where both of these things intersect, right? There's a point where both of these graphs meet, and it's this point right here. That point is at the coordinate of 1, 2, 3, comma, negative 1, 2, 3, 4. It's at 3, comma, negative 4. And so therefore, your solution to the system of equations is exactly that, 3, comma, negative 4. I think this really highlights the importance of sketching accurate and neat graphs. I did provide on our Google Classroom page some printable graph paper for you to use if you so desire. I think that's very helpful to just print out a bunch of it and have a bunch of graph paper on hand. If you want to order graph paper on a website like Amazon, it's not very expensive, so it's good to have around. I think you'll use it throughout your math career in high school. Or if you want to wait until we are in school doing actual in-person instruction, I hope that is sooner rather than later, but I will try to provide you with a good amount of graph paper then as well. All right. You could do it in your notebook if you want, but just make sure you are super neat and tidy when you're sketching your graphs. Okay, that's why it's worth it. Imagine if you just scribble this, it's not really going to be possible to see where that intersection point is. All right. Let's do one more example. This last example, we're going to, instead of finding x and y intercepts to graph in standard form, we're going to convert to our slope-intercept form and do it that way. All right. So consider something like this. We have, where's my example here? Right here. 4x plus 3y is equal to negative 18. And we also have x plus 3y is equal to 9. Okay, 4x plus 3y equals negative 18, and x plus 3y equals 9. Let's do this by converting to y equals mx plus b instead. Again, I'll do the first one in green. In order to handle this, what I would do is I'd say, well, I want this to look like, my goal is to make it look like y equals mx plus b. So if I'm starting with 4x plus 3y is equal to negative 18, to make it look like slope-intercept form, let's start by moving the x over to the other side. So I'm going to subtract 4x from both sides to eliminate it from the left and bring it over to the right. That gives us 3y is equal to negative 4x minus 18. And lastly, I would divide both sides by 3 to get y alone, because that's exactly what we want. We want just regular old y over here, right? That's going to give us y equals negative 4/3. Can't reduce it, just leave it alone, times x minus 6. Hopefully that made sense to everybody how we did that. Let's go ahead and sketch a graph of that one first on a coordinate plane. I'm going to draw my coordinate plane slightly off center because I know that this graph, I'm pretty sure the intersection point is like way over here somewhere. So I'm going to draw it slightly off center this time. Let's see how that works. So our y-intercept is at negative 6. That means we go down 1, 2, 3, 4, 5, 6 right here. And I would follow my slope by going down 4, 1, 2, 3, 4 over 1, 2, 3 right here. If I wanted to extend it in the other direction as well, I would go up 4, 1, 2, 3, 4, left 1, 2, 3. Let's do that a couple times. Up 1, 2, 3, 4, left 1, 2, 3. And up 1, 2, 3, 4, left 1, 2, 3. Maybe have something kind of like that. All right. Let's do the other graph in red. So let's connect this first nicely with a nice ruler. Kind of like this. There we go. That was actually quite good. I'm pretty proud of that, actually. And let's go ahead and do our second one in red. X plus 3y is equal to 9. Again, I want that to look like y equals mx plus b. So if I'm starting with x plus 3y equals 9, first thing I would do is I would subtract x to move it over to the right side to get just like I want here. I want that x on the right side. Gives me 3y is equal to the opposite of x plus 9. Lastly, we can divide both sides by 3, divide by 3, divide by 3. We would get that y equals negative 1/3 times x plus 3. 9 divided by 3, right? So we'll start at our y-intercept of 3. 1, 2, 3. And let's follow our slope of down 1 over 3. Down 1, right 3. Down 1, right 3. You might notice we're kind of trending away from our line that we want to intersect. So that may be a good indication to say, hey, let's try to extend it to the right. Or sorry, extend it to the left instead of to the right. So I can go up 1 over 1, 2, 3. Follow the slope in reverse to preserve that straight line pattern. Up 1 over 3. Up 1 over 3. I'm extending into the problem here. Up 1 over 3. And we end up with this line, which I'm going to have to try to draw my very best here. There's a lot of points to connect. Let's see, let's see, let's see. It kind of looks like that's pretty good ruler position. Let's do it. Point of no return. Here we go. Not bad, not bad, not bad. Okay, I'll take that. I'll take that. That's not terrible. And you notice that when we sketch a graph of that, our intersection point is way up here, but it does in fact cross. These do in fact cross each other. And that intersection occurs at, let's see, negative 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 9, comma 1, 2, 3, 4, 5, 6. That intersection point is at negative 9, comma 6. And so therefore, that would be the solution to my system of equations. All right. Again, I think this is a really good example of why it's super important to sketch a neat graph and why, if you can use graph paper, it's very, very beneficial to be able to use graph paper. If not, then make sure you please make some nice even units on your notebook when you do sketch the graphs of these, or you could print out the coordinate planes that I will provide for you. All right, so I'm going to upload some printable graph paper, printable coordinate planes. Please utilize those resources if you need them. The last point I want to make very quickly as we close out here, and I neglected to do it up here for this problem, is the fact that, again, you could take a couple seconds, check your work, and see, is this true? If x is 3 and y is negative 4, is this statement true? Well, 2 times 3 would be 6. 3 times negative 4 would be negative 12. 6 plus negative 12 is, in fact, negative 6, so that one checks out. How about the top one? X is 3, y is negative 4. 2 times 3 is 6, minus 4. Looks like it's equal to 2, so I'm happy there as well. With this bottom one, let's check our solution. Negative 9 is 6. With the top one, if x is negative 9 and y is 6, 4 times negative 9 is negative 36. 3 times 6 is 18. Negative 36 plus 18 is equal to negative 18, so that works. Bottom one here, x is negative 9, y is positive 6. Negative 9 plus 3 times 6 is 18 is equal to positive 9. So we're happy there as well. So it's always worthwhile, if you are able to, take those extra few seconds and check your work. So, quick recap. We talked about the idea of a system of equations when you have two equations working together, sharing the same set of variables at the same time. And in order to solve a system of equations by graphing, we really just have to graph both functions on a coordinate plane, like we saw here, like we saw here, like we saw here, and like we saw here, and find that intersection point. All right? A couple questions you may be asking yourself, or something maybe if you're not asking yourself, something I want you to think about in preparation for next class. What do you think happens if both of our equations never intersect? What if they're parallel? Something to think about. What if both of our equations happen to be the exact same line, one overlapped on top of the other? Think about that. Is it possible to have more than one intersection point? Something to think about. That's what we're going to discuss tomorrow. Okay? Thank you guys for your attention and focus today. I hope, again, you have a happy new year, and I'll see you tomorrow. Take care, everyone.